Welcome, dear learner. From nuclear physics, we are discussing about the radioactivity. In previous lecture, we discussed about specific activity. Specific activity is a activity of a 1 gram of a radioactive substance. Friends, in this lecture, we have to see partial radioactive decay. We know that the radioactive elements have unstable nuclei and therefore they can emit alpha particle, beta particle and gamma radiation. Some radioactive elements emits only alpha particles. Then it is the alpha source. Some radioactive elements are emits only beta particles. So it is a beta source. But some radioactive elements can be emits alpha particle as well as a beta particle. And it can be also emit gamma radiation. So here, if we consider there is a different mode of disintegration of a radioactive nuclei. The total decrease in a number of atoms. Total decrease in number of atoms can be represented as minus dn. It is equal to d n alpha plus d n beta. This represents total decrease in number of atoms. Okay, we know that n means number of atoms at a time t. Here we can represent n alpha. It is the number of atom at a time t. Okay, according to law of radioactive decay, we can say that the rate of disintegration of alpha particle can be represented as dn alpha divided by dt. It is directly proportional to n. Okay, a rate of disintegration of alpha particles. Okay, or rate of disintegration of radioactive nuclei for alpha particles can be represented like this. Okay, so this is equal to d n alpha divided by dt. It is equal to, this can be written as lambda alpha into n when we consider magnitude only. Here, lambda alpha represent decay constant for alpha particle. Similarly, rate of disintegration of a radioactive nuclei for beta particles can be represented as d n beta divided by dt. It is directly proportional to n, that is the number of radioactive nuclei at a time t. So this can be also written as d n alpha divided by dt. It is equal to lambda beta into n, where lambda beta represent decay constant for beta decay. Decay constant of a radioactive nuclei for beta decay. Okay, and therefore from this equation, we can say that dn alpha, it is equal to lambda alpha into n into dt. Similarly, we can represent, okay, this is for beta vertical. Okay, so d n beta, it is equal to lambda beta into n into dt. Okay, now putting this value in equation number 1, okay, putting the value of a dn alpha, that is disintegration of radioactive nuclei for alpha particle and disintegration of a radioactive nuclei for beta particle. In equation number 1, we get the total decrease in a number of atom, that is minus dn, it is equal to lambda alpha n dt plus lambda beta into n into dt. Okay, so this equation can be also written as lambda alpha plus lambda beta into n into dt. Okay, so this is the total decrease in a number of atom when there is a two mode of a disintegration, that is a disintegration of a alpha particle as well as a disintegration of a beta particle. Now, according to law of radioactive decay, we know that the radioactive nuclei are disintegrate exponentially with the time, and therefore we can say that n is equal to n0 e raised to minus lambda into t. Okay, where n0 represent number of a radioactive nuclei when t is equal to 0. Okay, n0 means number of radioactive nuclei when t is equal to 0. That is the initial radioactive nuclei. And from this we can say that the radioactive nuclei disintegrate exponentially with the time. Now, in this case, we consider two mode of a disintegration. That is, the radioactive nuclei can be disintegrate alpha particle, or there is a decay of alpha particle and there is a decay of a beta particle. And therefore, we can say that n is equal to n0 e raised to minus lambda alpha plus lambda beta into t. Okay, we can represent this like this. This can be also written as n is equal to n0 e raised to minus lambda total. Total means it is a lambda alpha plus lambda beta into t. Okay, now if we consider the ratio of decay constant for alpha particle and total decay, okay, total decay constant for alpha particle as well as beta particle, or simply we can say that lambda alpha divided by lambda alpha plus lambda beta. This represent branching ratio for alpha particle. Okay. Similarly, we can say that lambda beta divided by lambda total. So it is equal to lambda beta divided by lambda alpha plus lambda beta. This represent branching ratio for beta decay or beta particle. Okay. Now, the rate of disintegration of alpha particle can be also written as dn alpha divided by dt. Okay. So the rate of disintegration of alpha particle is directly proportional to the number of radioactive nuclei present at that instant. Okay. And therefore, this can be also written as it is equal to lambda alpha into n. Okay. Rate of disintegration is directly proportional to the number of radioactive nuclei present at instant t. Okay. Here lambda alpha represents the decay constant for alpha particle. Okay. But n is equal to n0 e raised to minus lambda alpha plus lambda beta into t. Or simply we can say that n is equal to n0 e raised to minus lambda total into t. Okay. So this equation can be written as lambda alpha. Here we consider magnitude only. Okay. N means n0 e raised to minus lambda alpha plus lambda beta into t. Okay. Similarly, the rate of a disintegration of a beta particle can be represented as d n beta divided by dt. It is equal to lambda beta into n. So it is equal to lambda beta into n0 e raised to minus lambda alpha plus lambda beta into t. Okay. This equation represents the rate of a disintegration of a alpha particle. This equation represents rate of a disintegration of a beta particles. Okay. So here we can say that each decay process is governed by lambda alpha plus lambda beta, because the atom or nucleides is not prevented from beta decay even if alpha decay is obtained. That is, we can say that if the alpha decay process is carried out, at the same time the beta decay can be also carried out. Okay. And therefore we can say that if there are a number of a decay mode, okay, then decay partial radioactivity of a radioactive substance, if there are a number of a decay mode, then we can say that lambda is equal to lambda 1 plus lambda 2 plus lambda 3 plus lambda 4 plus up to so on. Okay. Here lambda represent total decay constant. Lambda 1 is decay constant for first mode. Lambda 2 represent decay constant for second mode. Lambda 3 represent decay constant for third mode, and so on. Okay. We know that according to half-life, that is the time required to disintegrate the radioactive substance to half of its original value, that is a capital T, it is equal to 0.693 divided by lambda. Okay. And therefore we can say that lambda is equal to 0.693 divided by capital T. So this can be written as 0.693 divided by capital T. It is equal to 0.693 divided by capital T1 plus 0.693 divided by capital T2 plus 0.693 divided by capital T3 plus up to so on. Okay. When we take 0.693 common and cancel from both sides, we get 1 upon T. It is equal to 1 upon T1 plus 1 upon T2 plus 1 upon T3 plus up to so on. Okay. Where T1, T2, T3, this represent half-life for partial radioactive decay. Okay. Partial radioactive decay. Okay. that we can say that when there is a disintegration of alpha particle, the alpha particle can be disintegrated particular time. The beta particle can be disintegrated at a particular time. Okay, so here this represent half-life for partial radioactive decay. Okay, so this is related to partial radioactive decay. Partial radioactive decay, we can say that the radioactive nuclei can be disintegrated alpha particle, beta particle and gamma radiations. Okay, therefore total decrease in a number of atom can be written as minus dn is equal to dn alpha plus dn beta. Okay, here the rate of disintegration for alpha particles can be written as rate of disintegration of alpha particle is directly proportional to the number of radioactive nuclei present at that instant, and therefore we can say that dn alpha divided by dt is equal to lambda alpha into n, where lambda alpha represent the decay constant for alpha particle, and therefore dn alpha it is equal to lambda alpha into n into dt. Similarly, the rate of disintegration for a beta particle can be represented in the same way, and therefore this can be written as dn beta divided by dt, it is equal to lambda beta into n, and therefore dn beta it is equal to lambda beta into n into dt. Putting this value dn beta and dn alpha in equation number 1, we get minus dn it is equal to lambda alpha and dt plus lambda beta and dt. From this we can take a common n dt, and therefore we get minus dn it is equal to lambda alpha plus lambda beta into n into dt. Okay, according to law of radioactive decay, we can say that the radioactive nuclei can be disintegrated exponentially with the time, and therefore n is equal to n0 e raised to minus lambda into t. Now this lambda can be represented as lambda alpha plus lambda beta. Okay, and therefore n is equal to n0 e raised to minus lambda total into t. Okay, lambda alpha divided by lambda total, the ratio of decay constant for alpha particle to the total decay constant of a radioactive substance can be considered as the branching ratio for alpha particle. This is the branching ratio for alpha particle, this represents the branching ratio for the beta particle. The rate of disintegration of alpha particle can be written as dn alpha divided by dt is equal to lambda alpha into n, but n is equal to n0 e raised to minus lambda alpha plus lambda beta into t. So this represents as like this. Similarly, rate of disintegration for beta particles can be represented like this. Okay, we can say that when there is a emission of a alpha particle, at the same time beta particle can be also emitted. So there is a disintegration of a different mode, and this disintegration of a different mode is the partial radioactive decay, and therefore we can say that the total decay constant can be written as lambda is equal to lambda 1 plus lambda 2 plus lambda 3 plus lambda 4 plus up to so on. Okay, according to half-life, t is equal to 0.693 divided by lambda, we can represent like this. When we take a common 0.693 from the both side and cancel it, then we get 1 upon t, it is equal to 1 upon t1 plus 1 upon t2 plus 1 upon t3 plus up to so on, which represent partial radioactive half-life for a different particles, that is alpha particles, beta particles or gamma radiation. Thank you.